Today we're going to be talking about section 5.5, which is all about what are called linearizations. Now, the word linearization has the word linear in it. So basically think about this as writing the equation of a line. We're just giving it a fancy name. Let's review what we know about functions already. We already know that taking the derivative of a function allows us to find the slope of the curve at a single point. Now, this process is based on the assumption that if you zoom in really close, that even the curviest functions will look like a line. If you think way back in the semester, we actually took a function, we zoomed in a lot of times, and we said, hey, this one looks like a line, and then with this absolute value function, it doesn't look like a line. That must be why there's no derivative there. Using this idea, we say that a function is what's called locally linear. Local not meaning like, hey, shop local, but local meaning like really close. Now here's the new vocab. A linearization says that if a function is differentiable at a specific number, then we can approximate the value of the graph by looking at the tangent line near that specific number. So, if we know the equation of a tangent line is y minus y1 equals m parentheses x minus x1, and we decide to call our ordered pair a comma f of a meaning the y value, then by substituting that back in, we would have y minus f of a equals, instead of m, let's call that f prime of a. F prime meaning take the derivative there, because derivatives are how we find slopes of tangent lines. Parentheses x minus, and we're calling the x value a. Basically, by rearranging this equation, we can get y by itself. So we would have y equals, again we have f prime, so the derivative tells us the slope instead of m, parentheses x minus a is the x value. I'm going to add f of a on both sides in order to get the y by itself. And then what we do is we say, hey, let's call y L of x. L stands for the word linearization, equals f prime of a, parentheses, x minus a plus f of a. Now again, we call this equation the linearization, meaning make the equation of the tangent line at that specific x value. Here's what we can use this for. This problem says find the linearization of this function and use it to approximate this value without a calculator. Here's what you need to remember. Calculators are great, but calculators are not always around and have not always been around. So in order to estimate hard values like 1.02 without a calculator, it was easier for us to do that if we had the linearization, because the value of that x value on the tangent line is going to be very close to the actual y value that we're looking for. Let me sketch a little picture for you. If we're talking about graphing a function, and I find the tangent line to that function right here. Let's say I want to know the y value of the function at this specific x. Well, the y value of the tangent line is pretty close to the y value of the function. If you zoom in, you'll see that those green and blue points are pretty close together. So because the green point is pretty close to the blue point, the y value here is a good estimate of the y value here. Let me show you how to do this problem. I'm actually going to change the wording of the problem just slightly to make it a little bit more user-friendly. I'm going to change this, instead of f of x equals the square root of 1 plus x, to just the square root of x. And instead of x is 0, I'm going to change that to x is 1. because the number 1 is close to the number 1.02. Now let's try this problem. In order to write a linearization, I need a tangent line. And I know that when I need a tangent line, I need a point and I need a slope. So what point would I use? Well, it tells me in the problem that my x value is 1. It also tells me in the problem that my f of x is the square root of x. So if I take the number 1 and I plug it in there, I get 1 as my y value. Now to figure out my slope, I'm going to need a derivative. I'm going to think about the square root of x as being x to the 1/2. So I would have 1 over 2 x to the negative 1/2, which would be 1 over 2 times the square root of x. So the derivative at that same x value of 1 would be 1 over 2 times the square root of 1, which is 1 over 2. That means that my tangent line, which I'm going to move this down a little bit so you guys can see it. My tangent line, let me see if I can get this to straighten out a little bit. My tangent line would be y minus 1 equals 1/2 times x minus 1. In order to make this a linearization line instead of a tangent line, I'm going to change the y to an L of x. And I'm going to add the 1 on the other side. So 1/2 times x minus 1 plus 1. Now we're not quite done yet, but we're done with the first part. Get the linearization. Now what we want to do is estimate this number without a calculator. Now the number that we're trying to plug in to the square root function, the new x value that I'm trying to use here, would be 1.02. I'm not including the square root here because the square root is already part of the function. I'm just looking at what number am I trying to plug in. I'm trying to plug in 1.02. So all I'm going to do is plug in 1.02 to my linearization, wherever I see an x. Now, 1.02 minus 1 would be 0.02. Half of 0.02 would be 0.01. So my final answer would be 1.01. In other words, I'm estimating the value of the square root of 1.02 will be worth 1.01. Now, let's check it on our calculator. Let's see just how accurately we estimated. If I type in the square root of 1.02, I get 1.009, which if I rounded that would be 1.01. In other words, this is a pretty darn good estimate, especially considering that this is not a number I would know off the top of my head. Let's see if we can figure out how to estimate the square root of 123. Now it gives us a clue in the directions. It says use linear approximations to estimate. That's your clue that you're going to need the equation of a line. So if I want to write the equation of a line, I need a point and I need a slope. Now I'm trying to estimate the square root of 123. So the first thing I'm going to do is figure out a function with a nice answer that is close to that. So I'm trying to find the square root of something. I'm going to say that my function is the square root of x. And since a number that is close to 123 that I can easily take the square root of in my head would be 121, I'm going to choose that x value at which to write my linearization. So my x value would be 121, and the square root of 121 would be 11. Now to find the slope, I need the derivative. Again, I'm going to think of the square root of x as being x to the 1/2. So I would have 1/2 x to the negative 1/2, which is really 1/2 times the square root of x. Now I want to know that slope at 121. So 1/2 times the square root of 121 would be 1/22. Therefore, my tangent line equation would be y minus 11 equals 1/22 times x minus 121. In order to rewrite this as a linearization, I'm going to change the y to an L of x, and I'm just going to add the 11 on the other side. So 1/22 times x minus 121 plus 11. Now the second step here, after I have my linearization, is to estimate the square root of 123. In other words, my new x value that I want to plug into my linearization would be 123. Because my function is the square root, this is the number I'm trying to plug in. So my linearization value at 123 would be 1/22 times 123 minus 121 plus 11, which means I get 1/22 times 2 plus 11. 2 and 22 reduced to 1/11 plus 11, which means I get 11 and 1/11 is my approximation. So let's see what that would be. 11 plus 1/11 would be 11.09. If I actually calculate the square root of 123, those two numbers are pretty darn close together. This is a fairly accurate estimation, whereas if I had said to you when you came in today, what's the square root of 123, you might have said it's pretty close to 11, but you probably couldn't have been as specific as 11 and 1/11. Let's try one more. We're trying to find the cube root of 123. Now the function I'm going to use here is going to be the cube root function. And what I want to do is think of an x value that's close to the number 123 that has a nice cube root, which is going to be 125. The cube root of 125 is 5. 5 times 5 times 5. So in order to write a tangent line, I need a point and I need a slope. Now the point would be 125 comma the cube root, which is 5. To figure out the slope, I need the derivative. I'm going to think about the cube root as being x to the 1/3. So I would get 1/3 x to the negative 2/3, which would be 1/3 cube root of x squared. If I plug in the number 125, I get 1/3 times the cube root of 125 squared. Now here's where students panic. They're like, I can't do 125 squared. I don't want you to. So here's what you can do. Here's what interesting information. Squared and a cube root are reversible. I could do the squared first and then take the cube root of whatever I get as my answer. Or I could do the cube root first and then square my answer. Because of the nature of the numbers in this problem, I think doing that is going to be easier. The cube root of 125 would be 5. 5 squared is 25, which times 3 is 1/75. So my tangent line here would be y minus 5 equals 1/75 times x minus 125. If I want to rewrite that as a linearization, I'm just going to make it an L of x, and I'm going to add the 5. Here, you can't see what I wrote. I'm going to move that down. There you go. Copy that for a second. Now what I really want to know is what happens when x is 123? That was my original question. What happens when x is 123? So my linearization at 123 would be 1 over 75 times 123 minus 125 plus 5, which is 1 over 75 times negative 2 plus 5, which is negative 2 over 75 plus 5. Now, if I have 5 of something and I take away, that's why it's negative, 2/75 of that something, I get 4 and 73/75 left. So, how close is that to reality? Well, if I type in 4 and 73/75 on my calculator, and if I type in the cube root of 123 on my calculator, those numbers are accurate to the nearest thousandths. That's pretty accurate. So that's a pretty good estimation using a tangent line to get a value. All right, so we are going to practice this tomorrow. I will see you guys then. Enjoy your evening or afternoon.